Students, today we'll talk about tests of heteroscedasticity. So in this way you will identify whether heteroscedasticity is there or not. So I will be doing an elaborate video on this. The first one is Spearman's test. This is the rank correlation test. Everyone knows this thing. This is the most simple and approximate test for the detection of heteroscedasticity. So the first step one, okay, is regress y on x. You regress y on x, which is x is the explanatory variable. Okay, to obtain the residuals. First, you have to find the residual term, that is E, which are estimates of the distribution terms U. Okay. Now, next arrange, step 2 is arrange all these E, ignoring the signs obviously, and the values of x in ascending or descending order. Okay, so in ascending or descending order. Step 3 is, in order to compute the correlation between x and E, so now you find x and E's correlation. Okay, you need to work on this. And remember that summation of Ex is equal to 0 in the OLS method, ordinary least square method. So high coefficient result is, if it is a high coefficient value we have over here, then what does that mean? That means high coefficient value represents the heteroscedasticity is there. Okay. Yeah, it's present, and a very low value, very low amount of heteroscedasticity. So one can compute the rank correlation between the coefficients of EIs and one of the explanatory variable in case of more than one explanatory variable. So x1, x2, so you need to do it separately, x3 for this for more than one cases. Now I'm going to elaborate the second test. Okay, test 2. This is called the Goldfeld, one of the most famous one, Gold, G-O-L-D-F-E-L-D, Quandt, Q-U-A-N-D-T. This is done by the person who is also written the book of Henderson and Quandt, that Quandt. Okay, so this test is based on two assumptions. First one is that the number of observation is twice the number of explanatory variables. Okay, and the second thing is that UIs, all these UIs are non-autocorrelated and normally distributed. So this is the two basic assumptions. So the test involves estimating two least square regression lines. Okay, one using the first one using A, if I take, so the data thought to be associated with the low variance values, okay, low variance errors, and the other using data, and the other one is using data associated with high variance. So in the very beginning you are just segregating these two. So if the variances associated with each regression lines are approximately equal, if the variances are equal, okay, then homoscedasticity assumption cannot be rejected. Then homoscedastic. So GQ test, in short form we will be saying it. GQ test can be carried in the following steps. Step 1, I'm going to give you in a very basic way. Okay, throughout the years of studying it, so how I figured it out, I'm going to tell you. So order of observations, first is order of observations according to the magnitude of x. Second is omit a certain number of central observations, so removal of central values, say C. So the remaining observations, n minus c is there, observed and then divided into two equal parts. Okay, two parts. each part therefore now consistent of n minus c by 2 number of observations. One part include the small observations. Part 1 is small values of x, while the other is part 2 is large values of x. No problem with that. Now we are going to the third step. So what happens in the third step? So we have to fit separate regressions. So fit the separate regressional values. Okay. By which process? By the OLS method procedure to each part and obtain the sum of the squared residuals from each. So sum of squares SS with respect to the residuals. Done. Step 4. Now we have got this summation of EI square. Okay, so this is the sum of squared residuals from the step 3. Okay, and then will be two part, E1 square and E2 square. From the sample of, this is from the low values and this is from the high values. Okay, low and high, two things are distributed. So now we calculate F equal to summation of E2 square by summation of E1 square, which will have the F distribution. This will have a F distribution with n minus c by 2 minus k as the degrees of freedom, both numerator and denominator. So n is number of observations, c is the number of central observations which has been omitted, and k is what? Number of parameters to be estimated. So this is the parameters. Clear? So once it is been done, now your job is done. So if you are homoscedastic, the two variances, summation of E1 square, summation of E2 square, should turn out to be equal, and therefore F will tend to 1. F will tend to 1. Otherwise, it will tend to be a large, indicating the heteroscedasticity. Okay. Now, fifth step is H0 and H1, null hypothesis and all. So this is UIs are homoscedastic and UIs are heteroscedastic. So this is the three things. So if the calculated value of F in the fourth step is greater than the theoretical values, then obviously we will reject, or so calculated value greater than table value. So H1, calculated value less than the table value. This is the H0. So this is the thing. Now we move forward to test number 3. Is the part test. What is the part test? There are at least two limitations of the GQ test discussed above. Is that one? What are the problems? Number one is that it does not help us to obtain the pattern. Does not help us to obtain the pattern or form of the heteroscedasticity. So this is the biggest problem. Secondly, it does not test the presence of heteroscedasticity statistically directly. Statistically directly, it can't measure heteroscedasticity. Okay. Next one. So this test 3 is the Park test or the Park-Gletscher test. Park Gletscher test. So this removes the permutations and these problems. So for example, a functional form between the sigma ui square and the explanatory variable to do this. So this may be f of xi. So sigma square xi whole to the power beta e to the power vi. Okay. So now you take log. So sigma square ui, this will be log of sigma square beta log of xi vi. So here sigma ui square, this thing is not observable. So he suggests that ei square as a proxy. So use this in terms of this. So log of to the base ei square is log sigma square beta log xi plus vi, which is nothing but alpha beta ln xi and vi. So according to him, if beta in the above regression turns out to be statistically significant, if beta is statistically significant, then it would suggest a heteroscedasticity. That's it. So it's a two-stage. Stage 1, run the OLS regression disregarding the heteroscedasticity and obtain the EI from this regression. And step 2 is very easy. So run the log linear regression between ei square and xi and examine whether beta is significant. That's it. So this is the one. Next is step 4th. This is the Glaser test. Glejer. Again, Mr. Glaser comes in. So Glaser test is similar to the part test. Okay, the only difference is Glaser suggests as many as 7 functional forms instead of 1. So last time here a log linear formation, but here he hasn't used a log linear only, but many more also. That is summation of ei equal to beta xi plus vi, then mod of ei beta by xi plus vi, then this equal to beta root over xi plus vi, this equal to beta by root over xi plus vi, then it is alpha beta xi plus vi. Vi is in the error form. Another one is alpha root over this plus vi. Okay, so if beta in the above regression turns out to be significant, it would suggest the presence of this. So if beta is significant, leads to heteroscedasticity. Okay, in the data. So it should be clear in the above 4 tests that merely specify whether or not the disturbance terms are heteroscedastic, but not in the manner which they are heteroscedastic in a normal way. Okay, so these are the all possible tests of heteroscedasticity. In the upcoming lecture, we will discuss about different heteroscedastic structures. Thank you.